Today we'll do a demonstration of MDTools. I will use MDTools on Solidworks as promised. I will try to alternate Inventor and Solidworks versions from next webinars. And like I did in the last demonstration, sometimes I'm starting from HyDraw, other not from a schematic. Although I always have a diagram made on HydroCAD, today I designed this block without the intelligence that is built in HydroCAD. Let's just take a look at the diagram so we understand a bit. It's not complicated. It's just a manifold we normally put on a power unit where we have the pump inlet, a check valve, a relief valve on the pump. We want to filter, so we have a pressure filter. That's an Italian MP filter, FHB 050 footprint. I want an accumulator. I just had a 3D model of an accumulator, so we will see it assembled on a 1x2 BSP port. We have a shut-off valve, a ball valve, allowing for us to discharge the accumulator if we need. So basically we have two MHA shut-off valve, and then we go into the manifold or distribution of our power unit. So this is not complex stuff. Usually we have this kind of manifolds in power unit. So we start designing our manifold, and we go in MDTools. I'm using MDTools 975 in Solidworks. It's still in a beta, so I know we have some bugs, but hopefully I will not jump into them during the webinar. But I trust the software, and I did a lot of testing with it, so should be good. As always, we start with a block, and so the first command is block. Although you could select material and cross sections by material, let me just quickly start with a let's say 200 millimeter by 160 by 160. The filter is not that small, so then we will try to see if all components fit. Since this will be a power unit mounted manifold, I imagine that my power unit reservoir will be down here. And so I want a through bolt hole for my manifold so that it will be easier to fit into my power unit. So when you design manifolds with through bolt hole, it's always tricky to find a place for the through bolt hole. So a good recommendation is start from the bolt holes. So I start with, let's say M10. So with this command, we can just start with adding bolt holes. I take an M10. If you don't find the cavities you need, just quickly go to the library manager and add. So let's say in this case, I don't have M12. I can go to my library manager. And let me get back here. I go to my mounting holes. I take my TCA M10 and I can make a TCA M12 and the diameter will be 21 by 13 by 19 and the diameter here is 15 by 50. And we can do a save as. So by doing this, we quickly create all the geometries that we need by starting from existing cavities. So basically now, if I create my bolt holes, I will find also the TCA M12, but I want TCA M10. 4 pieces on the top face, and I want just 10 millimeters from the edge. When you click OK, now the drill holes are placed. I am now working in feature mode. In the new 975, you will see a faster feature mode. And if we move to the SolidWorks browser, as you can see, we have different icons. So we are using the advanced drill hole feature that is available in SolidWorks. Although this is usually faster in designing than 970, I still like to work in virtual mode when I started the design because I like really initially to to try and different configuration. So remember, if you wanted to switch between virtual and feature, you just click convert. You have a warning. This will jump to virtual mode. And if you want then to jump back to virtual mode, you click again convert. The difference, as you can see here in the virtual mode, is that we have bodies and not that feature. This is a lighter mode which allows a faster operation. So let's start placing components, and then we will switch to feature mode later. We go to the cavity library, and if you remember, there was a filter, which is probably the largest component in my system. So let's go to the cavity. It was an MP filter, an Italian brand. The footprint is an FHB 050, and it has 2 ports. The inlet, let me define a net. So let me quickly jump back to the diagram. The net is basically a list of ports that are connected in our manifold. So my filter is here, and let's say that this item will be called fin, filter in, and this net, the outlet, will be called P1, just with a port name. So the filter inlet will be called fin, and the outlet will be called P1. So with this in mind, we go here, take our filter. So the inlet will be filter in, the net name is fin, and the outlet is P1. If you keep using standard net names, they will show up as a drop down here. And these net names can be defined in the MDTools options. Under the cavity color, you can define net names and also specific color for same net name. It's very easy, so you can just click new and create a net called drain and specify a color for that net. Anything you add here will be added and will be available in our net. So now if I took a cavity and take a cavity, as you see here, I will have also the drain available. Let's go back to our filter, MP filter. So we say that the net is fin and the outlet is P1. The component is filter. Usually we use the item ID in the diagram. In this case, I just use a text filter. It will be easy to find out in my browser. I place my filter in the drawing and I can select a position, let's say 60, 70 millimeter. It's better always to start with precise position for cavity, so it will be easier to have exact position for all the components. Now, there was a check valve before the filter, and it was a Rexroth MSR 15. So we find this cavity here, and we go to the MSR 15. So a check valve has 2 ports. The inlet is coming from the P from a flange, and we call that net P, while the outlet is going into the fin, so the filter in. Our component is called check valve, and we place the check valve, let's say here, or maybe we could find, well, we see the colors. The orange will need to go to the orange, so this position is not bad at all. Let's leave it here, and we position at a good position, let's say 60 millimeter too far, 50 millimeter, 120. I see that there is not a good alignment here. This is a check valve that really quick, we can deepen, sink in the block, so we can add it and make it, let's say 16 millimeters. When you exceed the spot face, as you can see here, we have a warning because the spot down, the bottom drill must be increased. So yes, we will make it 150 millimeters. And now we have synced our cavity. Looks good. So for my design, this is something I never did in other demo. I will use conic plugs, NPTF. So in my construction plugs, in the settings, I will select my NPTF plugs. all sizes, add. So in my design now, I'm for all the construction plugs, I will use NPTF. Another setting that we have in the library, and which is here in the library, is that for the plugs, all my NPTF plugs do have a corresponding SolidWorks file. This works also for Inventor, no problem at all. But as you can see here, we have linked the cavity with the corresponding 3D model. So we expect the automatic plug assembly at the end of the design process. Now we need to connect the orange one. So we make a construction block, connecting this, and we position automatically. It is taking half an inch NPTF. That's good for the size. And I put it here in the center. And I want to center with the other cavity, so we can reference to this cavity at 0 on the Y. And as we see here, there will be a possible intersection with the dead area. So let's move on the X by 1, 2, 3 millimeters to the left. So now we have made our connection, orange to orange. It's not aligned. If we want and we have room, we can do align these two cavities. So then we have a center to center. As a general recommendation, when you design a block, wherever possible, make always center to center connection. Your manufacturer will thank you. Sometimes it is not possible, so of course there is always a compromise, but really wherever possible, try to make center to center connection. The inlet of our check valve is Flange, so we go to our Flange library. That was a 3x4 code 62 Flange. The net name, now that we have some net in the block, we can switch off the show all. So when you switch off show all, MDTools will show you only the net that are available in your block. So I take the P net and my port is P. And we insert here, we can rotate it, and we can position reference to the center of the cavity. As you see, when we click reference to the center of the cavity, dynamically we have a new origin here. And to make it aligned, just use the XY. So here you put 0, 0, and now the drill is in the center. You could control the diameter. 19 is good for my flange, so nothing has to be made here. Please remember that in virtual mode, we don't see the real geometries. We see the drills, entire drills, because as I explained before, we use the multi-body technique. So basically every cavity is a unique body. We will transform into feature later in the design. Let me save my block, and let's put it on the webinars, MDTools. That's our, okay. And now we have also the tank lines. So we imagine that there will be always our reservoir down here. And reservoir means tank line. So let's plan to put the flange down here, the tank flange that will be directly connected to the tank. And but after our manifold, there will be other needs, maybe another manifold somewhere else. So on the back of the manifold, we will put our T1 and also our P1. So if you remember the schematic that we had made, and that's it. We have the tank going to the reservoir, but then we have T1 and P1 that will be connected somewhere else in our system. So we need a good layout for these ports in our manifold. So let's plan to do it. We take our P1. So the net is P1 and the port is P1. And we place on the back face. Yellow with yellow, so makes sense to put in the center. Let's rotate it and reference to the other drill in the center. And we can make the connection by stretching one drill. Please remember, connect cavity is not working with the coaxial connection. It will work only with the 90 degrees connection. So when you want to connect the two parallel connection, you must use the stretch drill command. We go to the SAE 3000 and we take the 1 inch 61. The net is tank, and this is T1, which we put somewhere here. Let's put it aligned to the other cavities, rotate it, and we put a reference to this cavity at 100 millimeter 0. That's too much. Let's keep it 80 millimeters. So in industrial manifolds, sometimes really we do not pay too much attention to how small the block is, because it's very important to be able to maintain, to replace items. So sometimes the industrial manifold is larger than what you expect on a compact hydraulics, because really the need is different. Here we don't mind if there are some kilos more in the manifold. And let's say T1, that's tank, our tank. As I explained earlier, we want to put the tank down here. We want to connect to the tank line in the center, and on the Y we put it 110 millimeters. Always pay attention to X and Y. It will save time with modifying later the position of the cavities. So that's our tank line, and that's good. Now now we have made the skeleton of our block. We have the pressure entering in the check valve, going to the filter goes to the system, and then we have a tank returning back. We have a relief valve on the pressure line. That's a Rexroth DBD10K, which is basically connecting the P line to the tank line. That's our relief valve. We put on top here. Let's connect. And again, we can consider using the flange to connect here. So we can just position in the reference to this drill. And as you see, always dynamic change of the position. X we put 0. And on Y, we want to change reference here. So to have exactly center to center to the check valve that is down there. Okay. Now, instead of adding a construction port here, we want to connect directly the flange here. So if we connect, we just connect, this will reduce the drill of the flange, which we don't want. So we want to add an additional drill to our cavity. So the right command to add an additional drill is, well, in this case, as a generic rule to help manufacturing, we want to extend the large diameter in order to get out of the first intersection. And let's say we want it to be 65 millimeters deep. Let's make it 25, the diameter. So we want to extend, and then we started with the smallest drill. That's a good recommendation, because we want to have a clean center for the next drill that is coming in the operation of the block. We add a new drill for this cavity, and we don't mind which size. Later it will be the cavity, the destination cavity, controlling it. Let's make it 15. I don't mind. Now MDTools is asking where I want to position this drill information. So let's leave the drill operation here, and it will be combined with the primary drill of the footprint. The depth, let's make it 10 millimeters. No problem. Don't need to be precise here, because later we will do the connect cavity. So we click OK. Now MDTools is transforming that cavity into a multi-step cavity. In fact, with edit, now we see that our profile is made of 2 different drills. And now we can do the connect cavity here in the center. And that's okay. let's check the diameter. Let's say that we want to have a 14 millimeter diameter in our drill, but as you see, the destination drill is conditioned by the cavity. That's good. Let's move quickly, otherwise we run out of time. We had ball valves, MHA. The ball valve is the N10, and it's connected to the accumulator. So net A is accumulator, net B is P1. It's the yellow connection, and that's the ball valve 1, and we position it here. So we want the accumulator to be on the top face, so we need the top face to be free. We put the accumulator next here. So let's rotate, and let's move this ball valve. So we can drag the position and put it here, and let's make it 80 millimeters. And we want to connect these drills. The green one will be our accumulator, which we want in the center here. So let's go for a BSP port. The accumulator was 1 inch. The net is always accumulator, and we want the accumulator being here. And let's leave it at 25, 80 millimeter, 90 millimeter. And we want to connect them. And here we don't seem to be able to find a good room, so let's try here. This looks better. We want a construction port here with this drill, and it's a 1x4, should be okay. And we position it here. There is a bolt hole there, so let's move to the right. And we click OK. If you want to verify the wall thickness, you can just do the wall thickness check for all the block or between or around selected cavities. So let's make it between these two cavities. We want to verify if there is at least 5 millimeters. And here it is 3.1 millimeters, so that's not good. So we need to get some more material here. So a technique could be we move this drill down, not too much, and we make an inclined drill. So we take this, stretch and incline. We go with inclination to this drill, and let's make it 20 millimeters, 16 millimeters. Now this looks better, and we can stretch this drill and go and make the connection here. Let's check our schematic. So we do a connection check. With a connection check, we can verify if we made mistakes. Graphically, we don't see any mistake here, but by mistake, there could be an intersection between a cavity with a bolt hole. So like in this case, I am touching bolt holes. So when we do a connection check here, then we have problems. A bolt hole and a port are connected. There are other mistakes that we can make, and let's fix it. So for instance, we could have nets that should not be connected together. So like if we extend too much the green drill, then if we do the connection check, then this will end up with a wrong connection. So two drills belonging to different nets are connected. Let's get back to our connection, stretch up to this connection, and we make it 32 millimeters. That's good. Let's start placing the components. We still miss another ball valves, but let's try to make the feature mode, we want to start building the assembly. So to make the assembly with the MDTools rules, we must convert to feature. So when we click convert, MDTools will ask you if you want to convert the block, and we are going to make our feature block. So this operation will take a few seconds or few minutes, depending on the complexity of the block. We improved a lot the speed in conversion with 975, so this will not take much. And if you have any question, doubt, just feel free to post the questions. With MDTools on Solidworks, I always prefer to start designing in virtual mode because I find it more faster and more reactive in any case. So now the convert has finished. Well, this is, if you see the color not okay, you just edit and click OK, then it will recolor the cavity. You see now that in feature mode, we can see the real intersections of the drill. And if you remember, we had a ball valve on the accumulator that was connecting to the tank. Actually, that ball valve could fit here, and then we'll check with the lever in the assembly. But let's start making the assembly. So we save our block and make the new assembly. And then we get back to the design. MDTools provides commands. As I showed you in the library, I have linked 3D model of the plug with the plug cavities. So if we run assemble plugs on our manifold and take the block, which is here, now MDTools will find all the cavities that require a plug, and will just load the plug in the corresponding position. This block has not many plugs, but still for a block with many plugs, you will save a lot of time. So only 2 plugs here. One is here and the other is down there. Now we want to assemble ball valves, filter, relief valve, and so on. So let's do it. We can do the assembly interface. And for the check valve, we want to look into the Bosch Rexroth MSR 15K. For the ball valve, we need the MHA PKH. And on the accumulator, we want a fitting G1/2, and also we want a HYDAC plug SBO. This is one I used in the past for a design. Okay, and the filter, select and model. I have an MP filter. When you are done with all the link, you can click update. And now MDTools will take the components. When loading with the MDTools interface, you will see each file loaded twice. No worry, it's just an integrity check that MDTools does, and then position the components into the assembly. It will, in any case, save time because all the components are automatically mated and assembled to the block. So now it will start placing the components. Okay, this is our assembly. If you want, still you can assemble with the standard and in SolidWorks command, so you can insert components from any location. Like in this case, I may need to insert I have all the 3D models into my workspace, SolidWorks. Rexroth. Of course, everything that you do normally with SolidWorks will work, but then you will need to mate the components. So still maybe selecting and placing could be faster, but then you need to mate components. So you need to find surface and apply, and then not the dot. I want to mate again the cylinder with the cylinder. So technically you can use any SolidWorks command to assemble. Our block looks okay. We forgot a lever, so ball valve. So let's go back to let's save the assembly, and we go back to our design folder. So we can go back to our block, and we can place our MHA footprint. And now this is connecting the accumulator to the tank. So it's to discharge the accumulator. And the component is ball valve 2, which we can position here. And let's rotate the ball valve. Let's try to move it down. Actually, we can connect directly with the green and move it this way. Let's see if we can fit it exactly down there. We can align the drills always with the idea that we should make center to center connection, and we can make the connection here. We go back to the assembly, and yes, we accept. No major error. We didn't move anything in our assembly. Now we want to assemble the other ball valve. So always with the assembly interface, we take the other ball valve, MHA, and update. So this will automatically assemble the other ball valves. Now the lever is not in good position. So I'm using now a functionality of SolidWorks. I made some configuration. So I can select a configurator with lever 180. So this will apply the lever on the other side. And this is standard SolidWorks component. So this is a demonstration that really it's integrated in SolidWorks. So whatever you do with your components can be done. So here I want the lever at 270 degrees. And we leave the levers this way. We may need engravings on our block. So let's go back to our block. And so with engraving text, we can select a cavity, touch a face, and position the engraving here. So that's, for instance, our T1, which we want to position exactly at 145 and 90 millimeters. Engrave. And so on, we can go on to the other ports. P1. Engrave. And so on. We also have the possibility to compact a bit the block. So we can see that in the length, we can remove material. So by clicking block command, we can drag this and remove maybe 10 millimeters. Let me bring it back. Here I expect some problems, but we will fix later. So this operation has a small bug in 975 beta. So this operation will automatically remove material in between, and it can be used also to add material in between a block, and it will keep a consistent connection. Here it is. So the bug I was referring to is that the footprint is not following. So I just align now these two cavities. Again, if you'll see losing colors, just add it, but this will not happen then in the production version. And we do again connect. Stretch. Sometimes you may have, this is typical to Solidworks, Revolve Cut feature. In that case, just by adding 0.01 millimeter to a profile, it will have cavities. Solidworks is a bit particular with zero thickness geometry. So if you find cavities not showing up, you can just slightly change the position by 0.01 millimeter, or just changing the diameter slightly, and that will work fine. So now our block is okay. Let's look at the machining drawing. Of course, if we go back to the assembly, it will require update. No problem. In this case, we are not doing anything fancy. The block will update. Please remember that if you change phase to a cavity in a block, with MDTools commands, you will be able to make that cavity follow the new position in the assembly. If we want to make the machining drawing, let's do that. We take a paper, let's say A1. We do a create views, and we select our block. And we can define the type of projection. Let's leave these settings as they are. So with this command, MDTools is placing all the views of my block in the drawing. We see that it fits. So let's change a bit the size. Sorry, not here. That's the sheet. Properties, and we make it A0. So we have room. We can move views all around. All the views that are placed by MDTools have some characteristic: in, out for the filter, A and B for the ball valves or for the footprint. All the construction plugs are marked with a cross. We add dimensions with auto dimension, and this will add all dimensions to our block. In this case, MDTools is adding dimensions following your SolidWorks standards, and they are ordinate dimension from the X and Y origin of the block. As you see, I have good dimensions for my drills, although I did not really concentrated focus during my design to the position of the drills. Really, if you pay attention when you insert cavity and define the position and then use align command, then you will end up not having many cavities to move in the block after making a machining drawing.
If you do have any questions, this would be the good time to ask those. So again, use the webinar control panel. Thank you.
Now that the dimensions are finished, we can add machining callouts on all the cavities. That's one option. If you want to view all the information for the cavities directly with letters on each cavity, then you go for machining callout. The only operation you must do is you just move the cavity. So Rexo DBD 10K with a 10mm by 120 tip, and so on. Or if you prefer the drill chart, and in this case, let me opt for a drill chart so I can delete all machining callout. Before doing the drill chart, I will move to my block, and I want to assign machining ID. So this command will give to each cavity in the block unique ID. So let me stay with this numbering scheme: a letter for the face, letter for the cavity, and number for identical cavity in the same face. So this command will assign to each cavity in the block a unique ID. We go back to the drawing, and now we have the possibility to show machining IDs in the drawing. We can say show machining ID. So this command will display machining ID for each cavity in the drawing: AB1, AA, AC, and so on. And each face has a letter for the cavity and identical and number for identical cavities in the block. Now we can make the machining chart. Of course, it is possible to customize. I did a webinar recently showing how to customize it. Let's take my default. Let me just verify one option. Okay, the option is good. So I take the MDTools default, insert, and place my drill chart in the drawing. So in this case, it's a very compact drill chart because I'm using the quantity. I'm grouping identical quantity. So I have CBs, a dry seal, and PTF plug. But for instance, on the D face, I have 8 drills, 6.8 by 20, and M8. So the bolt holes for the flange. And again, so this is easy to handle a compact drill chart if you group identical cavities in the block. Something unique of MDTools in Solidworks is the possibility to display colors in transparency in the machining drawing. So if you want, and that's a very nice opportunity, you can create a machining drawing with colors showing the internal of the block. And that's interesting. Also, all the aspects in the Solidworks file are preserved if you open with eDrawings. So let me open the same block in eDrawings, and that's good if you need to view the internal of the block in the shop floor. So we can go to webinars and take our block. This is the block that we just designed. We can rotate, and we can also make cross sections according to plane. So this is nice, and because really you can check for intersection and so on directly in the with a viewer without the need for SolidWorks. This will work also in the assembly, so we could open the assembly directly. Let me do that. Let me open an assembly file, and the assembly will work as well. And if you then look into transparency, we'll see all the connection.